yes, the talk is kind of, I'm not, I won't say I'm winging it, but I have been working on this talk throughout this school because I feel that I feel that it might be valuable to provide some perspective and lessons learned, from my years of modeling with ERGMs and some ways of thinking about things. Now, obviously, George has given a brilliant introduction to ERGMs, and much of what I was going to say he has already said. However, I want to perhaps go into some a bit more depth and perhaps try to give you some intuition for why things work in ERGMs the way they work and elaborate on some things. Now, I don't know whether I'm going to take the entire hour and a half, which I think would be actually a good thing because, I'm holding up lunch. But that said, my current plan is basically I'm going to have some slides. I'm going to do a little bit of demo in our studio, just to show how we address some of these. And also, I am going to draw some pictures. Although, I suppose if I had more time, I would have done one of those XKCD style plots. Okay, so a bit about ERGM notation. I'm just going to use capital N for the set of actors whose relations are of interest, and little n for their number. Now, I'm actually going to, again, the focus of this talk actually will be unipartite networks, and most of the time they're going to be undirected, some of the time they'll be directed. Obviously, as Andrew mentioned, I've done a lot of work in weird networks, ordinal data, count data, and such, and perhaps if there's interest, I could probably also talk about some of that. But my main focus is just kind of very general thoughts about using ERGMs as a tool, in particular, and how to think about ERGMs, how to interpret them. So yeah, I have a data structure within a network. Yij is the indicator of presence, and Yi is the set of neighbors of I in its degree. Then, in order to model networks, of course, we need to think about what networks could have happened. Right now, this is a general thought. General, I guess, I don't know whether lesson. A network model is a wave, not a particle. And I know I make you. I hope the physicists in the audience aren't going to be too offended, but I think it's an apt analogy because, as we will see, a lot of the model estimation is characterized in terms of the space of possible networks, and how likely is each network in that space, rather than a specific network. And I think the more you think in those terms, the better your intuition around ERGMs is going to be. So you have potential relationships. Again, this could be bipartite. So if you have a bipartite network, for example, only some relationships are permitted. On the other hand, for example, if you're looking at a network of marriages, where, at least assuming in a society where bigamy is not allowed. By the way, I recently found out that bigamy it's not from the word big, it's bigamy, two spouses, something like that. Anyway. That was not. I did not find out. I did not find this out through personal experience. In case you're wondering, I'm actually quite boring. The point is that that's not how you could do this, because here you actually have to. This is just specific. Some edge types are allowed, some are not. But for example, if you have a multi-mode network. Right? You can also represent it in these terms, because when you have, say, people being employed by companies and people knowing each other, but companies maybe don't necessarily know each other, or maybe companies subcontract that people don't necessarily interact directly except to companies. It depends. So you could have more different combinations of that. Then there is. Then I use Calgraph pointer for the set of possible networks. Now this is where, now notice that I have this little notation here that it's a subset of 2 to the this blackboard white. That is So the idea is that it's this is notation from called the power set. Now, power set, the idea is the set of all subsets. So the idea is that we take the set of all possible relationships, and then we look at which of those relationships actually occur. And then the sets of all the possible sets of relationships that can possibly occur, that's our set of possible networks. Except that we might have further constraints, such as, again, if we're looking at, we can constrain the network to have one, every node to have one relation. We can, and now, and this is where George talked about some constraints, such as you can ban all triangles in the network by putting an offset term. This actually ends up modifying that calligraphic Y, right? It excludes some of the possible networks from that set. Right? So they can no longer occur. And then once we have that, we'll come back to sample space in another context. But this is, so this is right, nervous specification. You've seen this before, all day yesterday. Okay, so the point, but the first point is that the first thing to always keep in mind is that we always talk about the probability for the whole network. Right? We cannot look at one edge. We're not looking one edge at a time. And then, right, we have our parameters. Now we specify again. Sample space is a part of the model specification. Right? And again, this is some kind of a trivial statement, but it's also worth always keeping in mind. And then, of course, we have the vector of network features, which is important, or however you interpret that. Now, then I have this weird eta thing. Now, the eta thing is, the idea is this. You have, so far, at least what George showed you, you have, you basically have eta of theta is equal to theta. But it turns out that sometimes it's helpful to transform our parameters before multiplying them together with statistics. And I'll give you an example. Now, this is kind of, on one level, it's a province of fairly highly technical people in technical problems, and usually we just do most of the work for you. But it is also helpful to keep that, to keep some of those things in mind, and actually sometimes wonder, for example, if you might want to bind some of the parameters together in some particular way, in which case you might want to consider that as a tool. And actually in the ERGM package we do try to make it easy. We actually have an argument called parameterize, in which you kind of manipulate that thing. Anyway, so again, this dot, it means you take each element of eta of theta and multiply by the corresponding element of s. S is, and then exponentiate and divide by the, of course, the normalizing constant, which is often intractable. Now, so then again, we talk about microstructure, or global and local structure, and the bottom, I guess the way I like to think about ERGMs is, so you have a bunch of dials in front of you, right? You have maybe one day I'll actually sketch a picture, or maybe you have an LLM generator, maybe actually pay somebody to do it, I don't know. But you have a bunch of dials in front of you, right? This dial has a little edge on it, and this dial has a little triangle on it. We'll talk about triangles later. But this edge has a bit like one type of tie, homophilous ties maybe, and so on. And you can turn each dial, right? And you turn it one way, it increases the probability of networks with more of that thing, and decreases probability of networks with less of that thing. And turn the other way, it does the opposite, right? And but that dial, it doesn't just affect that particular feature of the network. It affects the rest of the network, right? If you increase the total number of edges in the network, unless you do it in a very, very particular way, you will probably also increase the number of triangles or number of whatever other structures that depend on having edges there. You will decrease the number of, say, isolates in the network. So everything affects everything, and I'll talk a bit more about the implications of that, and how I think about that. But one constant in that is that, and this is something you can actually prove very rigorously using exponential family theory, that if you turn one at a particular dial, it will increase the expected number of the corresponding network feature. So that's that E of E subscript theta, right? So if increasing the edges coefficient will always increase the expected number of edges. It might increase other things, it might decrease other things, but it will always increase. So you have these dials, and that's how I think about it. And again, this is a wave, not a particle. We're looking at a distribution of networks. There are all these possibilities, of which there are of which there are 2 to the, for undirected network, that's what n choose 2. Right, that's how many possible simple graphs of size n there are, and so we but every single one of them gets a probability assigned to it, and we're messing with the balance of those probabilities. But it turns out that we do it in a pretty clear way. Now, so again, George mentioned change statistics and change scores. Change scores are another name for that. So I'm going to elaborate a lot more on that because I think they're very, very useful for thinking about ERGMs on a whole bunch of levels. So just to recap, right, where do they come from? Well, if we look at the probability of a given edge, given the rest, and we take the logit of that, yeah. So logit, that's log odds, right? Log odds is the log of the probability of it being present divided by probability of being absent, right? P over 1 minus P, right? Okay, so we write that out in our, write out that formula, and it turns out we have these kinds of paired things, right? This is the network with the edge ij, added if absent, and in the denominator we have it removed if present, right? To force to zero, everything else being fixed, right? That's the notation we use for that. And then, of course, as George mentioned, conveniently, because we take a ratio of these two probabilities, the normalizing constants cancel. Okay, so anyway, the point is, conveniently they cancel, so we don't have to think about them. Then you can cancel the log and the exponent, and you can combine the bits and the exponent, and you end up with something that looks like this, right? The difference between the statistic with the edge present and it being absent, which means that, and log x cancels, so you end up with something like this, right? Oh, I'm sorry, this should be s's, not g's. I forgot to swap out the notation. Apologies for that. Okay, so so anyway, yeah, the statistic that is the value of it with the edge present versus absent, other things being equal. Now, again, George talked about it very briefly, but I think there's a very useful metaphor here, a very useful way of thinking about this, which now we have to, there's a limit to this metaphor, it's important. Now, like all metaphors, like all analogies, it has its limits, but I think this is useful for thinking about it. So you grab two individuals, IJ from the population. Right? I don't know. Esteban and Alejandro, just to make sure I'm not picking you on anybody. I'm picking on the most prominent people here, right? Or among the most prominent. With respect to organizing this workshop, how about that? In the social context, of this workshop, these are the least vulnerable people. Okay, so grab them, and we put them in a room together, and they're going to decide whether they're going to have a tie when they come out of the room. Now, they're going to look at these change statistics, right? So, and I'll give some examples in a minute, but these might include something like, do we belong to the same professional society? Do we have similar interests? Do we have common friends or acquaintances? Right? And And then they're going to put some weights on each of these considerations, some positive, some negative. Then they're going to evaluate that formula and either create a tie, or if you already had one, retain it with that probability. And otherwise, decide not to have a tie. And then we repeat from one. So we grab two more individuals, stick them into the room, and have them make a decision. Again, they look at what they have in common or what they don't have in common, so on. They put weights on them, they compute the probability, and they walk out of the room, either connected or unconnected. That turns out to, what I just described is a Markov chain Monte Carlo sampler for an ERGM, for an ERGM. And in fact, now it's not the most efficient one possible, but that is a sampler. Now, just to be very clear, this is not in itself a dynamic network process, right? We're not describing a real process that occurs over time. You could argue that a given network we observe at any given time, and maybe that I should have needed that one of the bullet points in the talk, but very often a network that we observe at any given time is a culmination of some kind of a temporal process that has led up to it. And sometimes you can even argue that, well, maybe you have this long-run process and we picked a random time to observe it, and maybe it's like a stationary distribution of that process or something like that. You can make that argument. I have made that argument because there was no better other way to model what I was trying to do. But I can talk about that later. But in and of itself, without much further assumptions, this is not itself a model for the process, although there have been efforts to make an argument that this makes sense as a model. In particular, one can sort of imagine that this kind of process has been going on for a long, long time, and in fact, you can imagine that if you do each time step this kind of thing happens, then then the stationary distribution of that process, the long run distribution of that process will be an ERGM, and that is what many of these papers discuss. So change statistics. Here's some examples. Now, I think you've seen one or two of these. So one obvious one is if we're counting the number of edges, right? That's the first one. Well, the change statistics is going to be 1, plus 1 if you prefer. Change is plus 1. Now, what if you are counting the number of ties incident on an individual that's blue? So you have some individuals in the network who are blue and some who are not. And we're going to count the number of ties incident on those who are blue. Any thoughts? I think I'll just give this one up. Okay, so it's the indicator. Again, by the way, this is my thing, is that it means for indicators. It's 0 if the condition is false and 1 if it's true. So if I is in the blue group, plus if j is in the blue group. So if both I and j are in the blue group, it counts twice. And the implication, going back to the formula back here, right, is that if you have a statistic like that, which counts the number of individuals. Now, so perhaps the sort of the global interpretation of this statistic in the context of an ERGM is to say that if you turn up this dial, you will have more ties incident on blue individuals, and of course the effect on potential blue-blue ties is going to be stronger than the effect on ties that are just blue on one end, right? So if you turn on that dial. So overall, you expect to see more of that in the network. You will probably also see more edges in the network, period, right? Because you are increasing the log logarithm edge in any case, or at least not decreasing it for any given network, for any given ij. On the other hand, locally it means that given the rest of the network, the probability of a tie is going to increase by some factor. I'll talk a bit more about that later, but e to the theta associated with this if it's if one individual is blue, and e to the 2 theta, or e to the theta squared if it's no blue. So at least for sparse networks. You could also do homophily. Again, there you have an indicator of that. And actually, yeah, these are too straightforward. So you just yeah, you just if it has a form of like sum over ij of something 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 times yi, you just drop the yi and you have a chain statistic, right? Right. So in that sense, a lot of it does really reduce to logistic regression because we go back to this expression. If all of these are just some functions of attributes y and j, well, you can write that on as logistic regression. In fact, if we that is what ERGM package does if you feed it that kind of model. It doesn't bother with MCMC. Okay, so on the other hand, you have ERGMs that induce dependence among relationships. There, now we don't just have something 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 times yij. So this one is actually for directed network number of pairs of I and j, and this is just so that you don't have because we only want to visit each each pair once of yi times j times yji. So that's a directed network. That's mutuality, right? So any ideas what the chain statistic will be for that? So the difference between two networks, one of them, so yji is fixed, yij goes from 0 to 1. How does the statistic change? Okay.
0.5, because it's doing that.
Yeah, well,
0.
Okay, so maybe how about this? Let's let's do the maths. Okay, I'm gonna just try to blank the screen. Blank the screen. Does the remote let you do that? Is there a screen blank? Oh, yeah, there is. Ah. Okay. Is there an eraser just so I don't ruin the rest of the talk? Yes, that's good. Okay. So you have the sum I less than j of yij, yji, right? So that's the number of times the relationship you have a reciprocated relationship, or number of unordered pairs of individuals for which you have reciprocation. Now, how I see the blanking is actually. So I didn't realize the blanking happened. I thought it would happen on the projector. So that's okay. Yes. So I thought my laptop was going to sleep. Okay. So now, just to make the notation a bit more clear, I'm going to replace these i's and j's with u and v. So u and v, u, v, v, right? Just so that it's okay. So now, so the change statistic for that is going to be, so we take so I'm going to explain this notation in a second. So the idea is these are indicators of presence of a definite ij, but with a plus ij means that if there's ij, if u equals I and v equals j, then force this to be 1, and this one's force it to be 0. Right? Makes sense, right? So now, well, first of all, in this case, we're summing over the diet, so we can just combine the sum, right? And also we can see, okay, so if u does not equal to I, or v does not equal to j, then it's not going to make any difference, right? The uv will be the same, and yv plus ij will be the same as uv minus ij, right? And with vu, if v does not equal to I or u does not equal to j, then they will be the same, which means that these will cancel most of the time, right? Right. So that means that really we're concerned with two cases. One is whether where I equals u and v equals j, and the other is where I equals V and U equals J, right? So, and of course, yeah. Okay, you know what? I think just for the sake of clarity, I'm going to rewrite it like this, because that way I don't have to worry about which one is what would become in, right? All U's and all V's are allowed. Okay. So so now we consider one case where I equals U, so there's I equals U, V equals J, or U, J equals V, and the other case is I equals V, J equals U, right? And we're summing up. So in this case, so if I equals U, J equals V, then this one is going to be 1, and this one is going to be 0. So this whole thing is going to be 0. So this is going to be 1. This is fixed at 1. So we just have Y, V, U. Now, because I and J and U and V are distinct, if this one is affected, then this one can't be affected, right? And conversely, here you have a case of Y V U, but then I equals U, V equals J, so we can write this as Y I J. One second. I think maybe I probably should have sketched this out in advance. Sorry, I'm blanking a little bit here. If we have I equals. Oh, sorry, J I, because this is fixed at 1 in this situation, and so this one is not, so we need to include it. But we know that I equals U and V equals J, so this is J I. Make sense? Okay, now let's look at the second case. I equals V, J equals U. Okay, so in this case, then this one is going to change. This one's going to stay the same, and by the same logic, you have Y, and again, this now U is J, V is I, so Y J I. So in other words, that's 2 times J I, and which happens to cancel with 1/2. So it's just J I, right? So. Now I know this was a lengthy way of deriving something very simple, but I think you kind of get the idea, right? We set up this calculation, and we set up this calculation. It gives us the local idea, and again, it makes sense, right? That means that conditionally, the chances that a relationship exists from I to J depends on whether there's a relationship from J to I. So, right, it tells you what it actually depends on. Let's see what else. Say anything else? No. Okay. Yeah. So what? And so that. Now, okay. So this is what I think. This is so the sum over the i's of. The sum over distinct, again, J less than K of Yij, Yik. So what's the name for this? Who knows this? What's the name for this motif?
Two selections?
2-star. So
right.
It's a
2-star, yeah.
Right? So basically we have for each node we look at okay, well, if you have node I, and then you have our various J's and K's here, so we look at this one 2-star, or is there a different color here? Doesn't matter. I guess it doesn't matter. Clear enough. 2 2-stars, 3 2-stars, right? Mm-hmm. So I mean, really, I could have replaced this with degree. I think away I choose 2, right? Which is so. And in fact, if we were to look at the change statistic for that, it will look something like this. Now, actually, I think there's probably a better way. I think, in retrospect, I could have just written this as the degree of yi minus yij, degree of yj minus yij. The reason is that basically the logic here is that if we have, and we could do the algebra for this as well, but the logic here is that if we have, again, say 3 edges already, if we add another one here, well, it's going to form a 2-star with this edge, a 2-star with this edge, and 2-star. It'll form a 2-star with all the existing edges. So that's the change statistic for that. Then this is an example of a specific degree count statistics, a number of nodes such that that have degree of exactly 1. This is what the change statistic looks like, and it's kind of, again, I probably should have used a more concise notation here. Typo here. Oh, oops. Yeah. Okay. Actually, sorry. This should be I, and this should be J. So yeah, I'm just going to draw right over that. Apologies, I made a typo here. But the idea is that it's, loosely speaking, it's that without this edge, without the edge that we're possibly changing, is the degree of this node I 0? Because if so, adding an edge will make it 1, right? Thus incrementing the count. And if it's already 1, then adding an edge will make it 2, and therefore reduce the number of edges that have degree 1, right? And we have to do the same thing with J because we're affecting the degrees of 2 nodes every time we add or remove an edge. Make sense? This is actually convenient. This is the whiteboard and the. Okay, so triangles are very favorite statistic ever. At least if you look at the pure maths literature. Okay, well, one way of writing that is the sum of I less than j less than k of yij, yjk, yki. So, again, this is an indicator of that. Now, so the change statistic for that, there's a number of different ways of writing it. And again, so sometimes you have to do the algebra. Right? I do the algebra, I show you how to do that. You could do something similar with, we have triplets of things. But I think maybe it might be, but just as with 2 stars, it might be more helpful to draw a picture. So if we have our I and j, we have some other nodes that they are potentially connected to, right? And some of them are something like they're a little corner of the network. Drawing that. I don't know, whatever. So the point is we want to potentially add an edge between them. How many new triangles will be formed by adding this edge? Well, how many triangles will be formed in this case if we just add this edge? I hear somebody whispering. 2, yeah, 2. 1, 2, right? And no, if there was a third node that they already both had a connection to, then it would be 3, and so on. Which suggests that there's a formula there, right? For we sum up over the potential third party, how many instances are there that I is connected to the third party and J is connected to the third party, right? Makes sense. Now, one major implication of all this. Now, remember this Gibbs sampling thing, right? Right. So, the probability of a given edge given the rest of the network depends only on the change statistic, right? It doesn't depend on the whole statistic. And that's great for computation because in all cases, so here, if you wanted to evaluate this statistic, in principle, now obviously there are more efficient ways to do this, but in principle that's an order and procedure, right? Order and square, so procedure. So that is it. The number of things you have to sum up is the number of potential edges. Now again, there are more efficient data representations, but again, in principle, it could involve up to that kind of a sum. But the change statistic, that's just one that you just need to check for membership in a set, assuming that's it. So it's basically that the order of magnitude of computational difficulty is on n squared lower. I'm trying to avoid proper computer science terminology because there's no point that here. But the point is, this is also why change statistics are important for not just for understanding networks, but also for actually fitting them. In fact, if you look at how ERGM is designed at the bottom of it, in order to implement a new term, the most important thing, the most difficult thing is implementing the change statistic efficiently. Now, for dependent ones as well, right? Here you have to sum up over 3 entities, right? Triplets, right? But now you only have to actually sum up over 1. Again, assuming that you need to only sum up over potentially n things, right? So that's another aspect of that. I should probably check the time because okay. Yes. Okay. I was worried I didn't have enough talk for the time allocated. Okay. So now this brings us to with this tool in place, let's think about triangles and why they are weird. Now, again, George talked about how often estimation fails with that, but my view, and again, he's absolutely right, but my view is that the estimation fails because, well, the model fails. The model is bad. So here's the thing. So this is the model. This is the kind of the model that's probably the most studied ERGM anybody, which is the edge count plus some coefficient times the triangle count. And of course, we're most interested in the situation where we have a sparse network, so the coefficient of edges is negative, right? If it were 0, then you'd have a dense network, so density of greater than 1/2. Usually it's much less than 0. And we have positive triadic closure. Right? Now, there are situations where you might have negative triadic closure. One example might be direct flights between airports, right? Because if you have if you can indirect flight, or actually trains, subway stations, or direct routes between subway stations. Because if you have a direct path, then there is less incentive to have, if you have an indirect way to get from I to J, then there's probably less of a point to get to creating a direct path. Right? So, but the point is, in this case, this is the most studied example, right? Okay, so the change statistic looks like this, right? It's +1 for edges, and then the triangle, right? Now, what does that mean? Well, okay, the probability of an edge other times unchanged is going to, I just plugged in, right? Theta 1 times the j is 1, and theta 2 times, again, the number of common neighbors of I and j, right? Okay, now, inverse logit, when, again, I can show you the math if you like, but when the network is sparse, so it has relatively few edges, when the probability is, when this input is negative and reasonably low, we can approximate that with exponentiation. So think of this as like we are forming first few edges and then what happens. Okay, we have exponentiation. That's much simpler. We can do some algebra on that and write it like this, right? E to the theta 1 times e to the theta 2 to the power, right? Because the product in the exponent means you can exponentiate the one bit and then exponentiate the result with the rest, right? So, in other words, we have this coefficient. Now, this is going to be greater than 1 if theta 2 is positive, right? and the exponent is common neighbors. Right. So what does that mean? It means that the probability of the edge, if they have no, given the rest of the network, if there are no common neighbors, is going to be just e to the theta 1, right? If they have one common neighbor, then we multiply this probability with e to the theta 2. And let's say that theta 2 is, I don't know, log of 2, so e to the theta 2 is just 2. So let's say we double the probability of an edge. And if they have two connections, we do 2 squared, so 4, 8, 16, and so on. So in other words, the probability, the predicted probability of an edge, given the rest of the network, grows exponentially in the number of neighbors. How is that realistic? Common neighbors. Is that realistic? Like what kind of a social system would produce that kind of growth, or that kind of for what kind of social system does that make sense? Now, as it happens, there are such systems. They're just not social. There is work, and I forgot to say the reference here, but this work by Carter Butz's group. They were looking at I think amyloid plaques, and well, basically these proteins that clump together in a particular way, and there you do actually can have this kind of this exponential effect. But in a social system, I mean, if you have three friends in common and you still aren't friends, then there's probably some countervailing factor that is important enough to prevent that. But whatever that countervailing factor is, does that mean that eventually an exponential growth will probably overrun that? So in that sense, no matter what, you're going to get a connection. But these are conditional probabilities. So, and this is getting a bit later. I'll get back to this later when I talk about degeneracy. What happens then is, let's say you're doing that thing with putting people in a room, right? We're back to this putting people in a room exercise. So let's say that at some point people decide to be friends. Okay, great. Now that means that, and it just so happens that this is IJ, so sorry. IJ, so they decided to be friends because they have all these triangles in common. But by doing so, they've now created another potential triangle here, right? And let's see, do they create another potential triangle here and another potential triangle here, right? Which means that they've, in our case, doubled the probability of a whole bunch of edges, right? And then when next time these two people are in the room together, they have a much higher chance of being friends, or coming out to be friends. And then another group of people, so Tom Snyder's in the 2006 paper characterized this as an avalanche. Again, I'll talk more about degeneracy later and a bit about the history of that. But the point is that it means that if once two individuals are once there's a critical mass, you just have more and more ties. Now, here, and again, I'll come back to this when it comes to degeneracy, but here again, think of the network model. It's a wave, not a particle. Right? What we're really saying is that each network, not each edge, each network has a probability associated with it. So now we're saying that if we have these networks with lots of ties, lots of triangles, they're going to have, that means that those networks are going to have very high probabilities associated with them because they have all these nice exponentially growing positive factors. And again, going back to this bit, the bit even earlier, right? And as we see, that effect can be exponential. So you end up with some networks, but also but also if at that critical point INJ decide not to have an edge, well, that's fine because that means they don't encourage any more networks. So maybe the social process will stay in an area that is sparse. But again, is that realistic for a social system? right? Is it that do our social system could the social process have just let me finish the sentence now. Could this social process have produced either a network with almost no triangles or a network that is a complete graph, but not something in between? And you got a question?
Could you repeat the example that you gave for a system that does work like that with this exponential?
How about I think probably easiest I should probably send the paper because I'm not well qualified to describe it. But the idea there was that you have the nodes were I think atoms or some small molecules and edges were chemical bonds of some kind. I think and they're basically and I think the idea is it was like a polymerization process. So when you had crystallization or polymerization process, so you had like that. The bigger the structure, the more attractive it is because the stronger electrical moment or dipole moment. Something like that. I'm not a physicist. There are physicists in this room.
No, I was this phenomenon of degeneracy only occurs to triangles or.
Okay, so it affects any situation. It can potentially affect it. So first of all, and again, I was going to talk about this later, but I think degeneracy is a misnomer. I think degeneracy is a symptom. It's not, but it doesn't describe the phenomenon accurately. Now, the true star kind of has a similar effect, right? The more edges you have, the more edges you create. So again, how about I come back to it towards the end? I don't actually have particular degeneracy slides, but it is something that is. Maybe I should skip to that. But actually, no. There's another thing I want to talk about before I talk about degeneracy properly, because I want to put it in the context of estimation. Okay. So what can you do about it? Well, this is just a sketch of what one might be able to do. So instead of having triangles, we can have this kind of a mysterious structure which looks something like this. Now, first we define this thing called this alpha, which is going to be a decay parameter. Now notice that if alpha here is 0, then actually then this whole thing is going to be 0. So this whole expression is going to be sorry, not the other way around. If alpha is 0, then this is 0, then this is 1. So we're just summing up. If it's if alpha, the bigger the alpha gets, the bigger the alpha gets, the closer this becomes to 1, the smaller this whole thing becomes. And now, why is that useful? Now, again, there is some algebra, but I'm not going to bother with it. And this is actually to counterbalance this effect. But the point is, you have, and then this item, that's the presence of the absence of an edge, which we saw before. And you can actually replace it with other things I'll show in the next slide. But basically, here, xtp is the number of 2 paths of some specific type for x. So in other words, 2 paths is another word for this kind of thing, right? Because if you have a directed network, there are different kinds of paths. Like you can have this kind of path, or you can have the path that goes the other way, or you can have outgoing thing. So that's why I talked about this. But the reason why we might want to have this kind of expression is the. I'm sorry. Okay, okay. There's an error in this. I'm sorry. The legend is not right. Okay. Yeah. Okay. My apologies. This is correct. Okay. So the idea is that this is the number of transitive paths of the exponent here, and the risk is the effect, which is basically the expression that's after yij, or actually it's everything. It's the expression e to the alpha, and then everything after ij. So if alpha is very big, then you basically have a linear effect. So in other words, if you have two transitive, if you have say two transitive partners, so two paths here, then you get number of 2 paths times yij, which is number of triangles, right? Or the number of 2 paths times wedge through number of triangles. If alpha is not like 20 or greater, they're just generally small, then actually it falls off, right? The effect of having additional 2 paths is going to decay. So instead of having this exponential thing, instead it actually decays a little bit. It's not quite exponential. The net effect falls off, which means you end up with something a bit more modest, right? So you don't get that kind of runaway effect potentially, which might be a more realistic model for triclosure. Now you can do something similar with 2 stars, and that's called geometric degrees. Again, maybe you can talk about that later if you like. Now the other thing is, by the way, so it's like 2 paths here, but what I mean is something like this. There are different ways of different kinds of 2 paths we can talk about, and also this Yij, we can actually replace it with, we can either say, for example, we can count, this is called edgewise, so request, for example, that refers to like structures that look like this, and this is outgoing 2 paths and incoming 2 paths, so this is for a directed network. It's hard to see the green arrow, but but here the outgoing creates transitive ties. So, and I'm going to draw a bigger thing here, just to be clear. So, 2 paths ties look like this. Right, so transitive ties, so there's transitivity here. And and I think this one of the groups was working with this, that represents a hierarchical kind of structure, because, for example, this represents a adoration or advice or something like that. The status of this individual is going to be, I don't know, higher if it's a positive thing than the status of this individual, right? On the other hand, incoming 2 paths, we would reverse these arrows. So this is think I and J. And this is reversing those arrows, so this is cyclical, so it's anti-hierarchical. Right, now there are other versions. For example, you could have a 2 path that looks like this, a structure that looks like this as well, which can be distinguished from others under some conditions. But again, I don't want to. I'm already running a couple of times than I thought I did. One trick, and actually this is something that might be useful. So it can actually be difficult to get these to work very well as well. And also there is an argument for including, so diode-wise here, this is the idea is that we're not going to check if there's an actual tie between them. We're just going to look at how many common neighbors they have. And that's also useful. That's something that you can sometimes model, particularly in the bipartite network where you can't have an edge here, right? You can still think about these things. And but sometimes you might want to think of this as non-edgewise. So that's thinking about, well, how many people, loosely speaking, have lots of friends, common friends, but aren't friends with each other, right? So that's a measure of social tension. Now, there you can model this as kind of a increase in the tendency to have to be friends if you have common friends, versus a pressure to the tension in not being friends when you have friends in common. So, a brief aside, curved ERGMs. So this is questions. Okay, curved ERGMs. Why am I bothering with these zetas? Well, it turns out that sometimes we just fix the alpha and something that makes sense. But sometimes we want to estimate it. So here I replaced alpha with theta 2 for notational convenience. We have that expression, it's the same as before, except I added theta 1 at the beginning, right? So we have some strength of the effect, and then we have the decay of the effect. This, by the way, this you do with the West fix equals false. Okay, so we're gonna transform this a little bit. This is the exact same expression mathematically. But except that instead of summing over the potential edges of Yij, and then this expression to the power of xdp, we're going to just consider all the possible values xdp could have, and plug them in here, and then check whether in this particular case that particular k applies, right? So you can. So what does that get us? Well, it gets us that we can. Oh, and by the way, k starts with 1 here because when you plug in 0 here, well, you have 0. This the whole thing to the 0th power is just 1, so 1 minus 1, so it's always 0. That's fine. Okay, then because it lets us rearrange things in such a way that we pull the sum outside, and then we have just the parts that depend on theta, and then just the parts that depend on y, which means that we can now write it like this. We can write it as a product of the eta of thetas and the product of s's and y's, and it turns out that we can then use some ergom computational machinery for that. Okay, so that's an overview of the change statistics and some of their implications and how I use them to think about ergoms. Any questions? Okay, so this one is actually, the rest of the sections are actually shorter, so I think we might still finish in time. Likelihood estimation. So this is, I'm going to skip, I'm not going to bother with the algebra if you like. I can bother with the algebra, but you have likelihood, right? That's just the probability. I just dropped all the extra bits. And you have you take the log of that. And now, if you differentiate this, right, because, as you might, if you have your intro calculus, you might remember that if you wanted to maximize some kinds of functions, the first thing you do is differentiate it. So we do that. And we actually end up with something interesting here. Now, I'm not going to explain why this is. I can do some whiteboard, but but basically, the eta of theta becomes this bit. But the main thing is that as you have s of y, and then you have minus, and it turns out that when you take the log of the normalizing constant, you end up and take a derivative of the log of the normalizing constant. It turns into the expected value of the sufficient statistic. So under the model. Now, again, we can prove this. I have slides that prove this, but somebody proved it like 70 years ago. But the point is, in fact, if you say eta of theta is just theta, then this becomes just 1, and so you end up with s of y minus the expected value. Now, that's so the main point here is that if now obviously we want the 0 to find the theta that makes that function 0. And the function, the theta that makes that function 0, and again ignoring the eta prime bit, is the one where the observed value of the sufficient physical network of the features that we put into the ergom matches the expected. That right? And then now, if you wanted to look at the information that is. Loosely speaking, how much do we know about the parameters? Well, again, more algebra, but the main thing is that that ends up being the variance of the sufficient statistics. So how much do they vary over the sample, over the sample space? And actually, I'll come back to that later when I talk about missing data. Now, so the main implication is that under the MLE, one nice thing about ergoms is under the MLE, you reproduce on average the observed statistics. Right? That's useful in a number of situations. In particular, you don't actually need to see the network to estimate to fit the model if you have the sufficient statistic. So that enables some interesting things. And so in an ergom package, if you pass the target.stats, it'll actually ignore what the edges in the network and just find the parameters that correspond to the sufficient statistics. Now, this is useful in a particular setting that I work in, which is egocentric data. So this is the network, right? We might call it guided census. And we might call this means the egocentric census, but maybe we don't actually get to see the network. We only get to see that, there's a certain number of reds who report tied to a blue, there's a certain number of reds that report tied to 2 blues, and so on, right? And then we have we observe a sample of those. So then, what we might have, but from that we might be able to say, okay, well, we observe 7 red-blue ties. Now, each die will be observed twice, once from each end, so we divide by 2, and then we multiply by the sampling rate. And that gets us an estimate of the sufficient statistics, so we can actually fit an ergo to the complete network, and we can do it for others as well. And we can then use that to simulate what the network might have looked like. We will never actually find out who is connected to whom, but we will reproduce the large-scale features of the network, right? And we will also be able to interpret the feature, have a local interpretation. So that's another implication. And again, I think maybe I'll pull up R and talk and do a quick demo here, but. Another implication is that if you have two statistics that are positively correlated, because we take a matrix inverse here, of the variance, right? If the chances are the estimates are going to be negatively correlated, and this is again something that George showed you the other day, right? When you add this is related to the idea that you add an edges statistic, you add a homomorphic statistic, the edges statistic went down, the edges parameter went down, right? And in fact, that's a related concept. Also, the other thing is again multicollinearity. If some statistics set up to others, then the variance is not invertible, and you can't estimate them uniquely. But the thing is that reasoning also applies to chain statistics. And here I am going to take a very, very brief, create a very brief example. So we're gonna. This is not big enough. Library ERGM. I'm going to use the Foamy as a high data set. And I'm going to fit an ERGM. And a formula that's so edges plus node factor grade. Right, so we have edge count, and then you have node factor grade. But if we look at the set of grades in the network, so this is. There are actually 7 of one of the grades, right? So in fact, one of the grades has been omitted, and again, George mentioned that. But it's omitted, and in fact, now this is something you can do in so nodal attributes. There is a sort of common way to specify nodal attributes, and there's a bunch of examples. But one of those is that if we look at node factor, it has an argument levels, and it defaults to -1. That means remove the first level. So what happens if we, actually, summary F, so ERGM. So then we have the coefficients, right? Now, we could say, true, let's keep all the levels. Right? So in fact, so I'll let you read the documentation. It is actually a pretty useful way of manipulating and specifying nodal attributes. But in the interest of time, so this is, now we include all the levels in the summary, right? And if we fit the ERGM, all of a sudden one of the coefficients is an A. Now, this is because this model is diode independent. We can actually detect this at this level, but we also get a warning. The following linear dependence detected among level statistics. 2 times the number of edges is the sum of all of the non-factor effects. So I don't know how much time of people and computers, including my time, has been wasted because somebody didn't notice that they specified a model that had multilinearity. Right? Now, even though, funnily enough, this is something that we would never do if we were just doing regression, right? Because this is one of the things we can start know intuitively when we study linear or generalized linear models, right? That yeah, of course, if you in R, if you were to specify a linear model with a categorical predictor, well, yeah, of course it'll drop one of the levels in order to make it identifiable, or if you specify it in a particular way, drop the intercept. But for networks, you kind of like forget that, even though we always know this, right? So, and this is why, again, thinking in terms of change statistics, thinking about in terms of not forgetting everything we knew about regression when we do ERGMs is very important. Right? That was one of the points I wanted to make. Now, the good news is, again, there's now. If I were to fit a model with data-dependent effects, it wouldn't do that. It would actually it would either fail to converge, or it would produce distribute the effect. It'll produce some. Basically, it would fit the model, but it wouldn't. Actually, maybe I'll demonstrate this, or I might have 10 minutes one way. So this tells it to forget that it's data dependent and just use the MCMC. So notice that it warns that the Hessian matrix is singular, etc., etc. It warns that the linear dependence has been detected, and it does actually return estimates for all of them. But if you compute them, it turns out that if you add them up in a particular way, you actually get the estimates you would have gotten if you had not included the extra effect. So that's something, again, we try to warn you, but it is something to keep in mind and not forget just because you're doing networks. I can kind of see this is very briefly. I don't know whether I'm going to bother with the demo, but just briefly how to think about this. Again, George talked about two kinds of zeros. Relationship is present, or it could have been present under the model, but was not, right? But it could be forbidden, right? In bipartite network within group ties. Incidentally, so there are different ways of doing this. One is, again, using an offset. Another one is using constraints equals and then fixed as or some other constraint. Now, remember how George brought up a list of ERGM terms? Well, there's a similar list of ERGM constraint. So sample space constraints, which explains how to specify them, et cetera, and here are all the different constraints. Some of them are more complicated, like the fixing the number of edges, which requires special treatment because if you want to fix the number of edges, you can't remove an edge without adding another one somewhere else, and vice versa, right? But for some constraints, there's also a way to specify a constraint based on an ERGM term. To say that, hey, when this ERGM term has a non-zero change statistic, don't allow that edge. Or do allow that edge. Okay, so if it's unobserved, it's missing data. Now, again, very briefly, this is actually not. There's actually some useful intuition here. Now, this is what it might look like. Now, there are actually different kinds of observational limitations, but I'm going to focus on this one, just the edge one. So this is an example of an ego net from a household. So the respondent, number one, told us that they're not connected to some, that they're connected to others. We don't know the ties among those who are not in the sample, right? If in fact this y of y ox is just telegraph of y, that is just the full sample space, that we don't have to know anything, this variance, these two variances are equal to have zero information, and everything in between, right? So there's another nuance here, which is that if we lower the variance, Now, how to implement it? Actually, I'm going to skip this part. Okay, last item, degeneracy. So, yeah, so we can you could see the paper, the section of the paper where we actually explain the history. But basically, degeneracy is, in my opinion, a misnomer. What happened was that, so in the 80s, you have Frank and Strauss and others saying, hey, we can have these Markov graph models, and actually even back then, I think Frank actually, these things are a little bit attractive, but we approximate them pretty well using pseudo-likelihood. Now, pseudo-likelihood, the idea there is we kind of, remember how we have that logistic regression-like thing with conditional given the rest of the network? Well, if we were to pretend that it's not given the rest of the network and just multiply those together, we actually get what's called a pseudo-likelihood, and we can maximize that and actually get decent estimates some of the time. Now, so people have been doing that, and then in the early 2000s, people started simulating for these networks, and they found that when we stuck, say, something like a triangle on the model, well, pseudo-likelihood won't tell you that there's this avalanche because it only looks like one step away, right? It looks at the immediate edge. But when you actually start simulating this, you end up with these kinds of these avalanche effects, and that so the people ended up seeing networks that were complete graphs, simulating networks with complete graphs. So that's, and when you have probability distribution where only one outcome is possible, or has a probability that is non-zero, that's called the degenerate probability distribution. So that's where degeneracy came from. But degeneracy is just a symptom, right? And ill-fitting it's also a symptom. So let's think about, you guys start to think about it. So recall that under the MLE, observed is always expected, and in many terms like triangle, truth towers, and others with positive coefficient edges and edges. So what does that mean? So I'm going to I think I can do this in 2 minutes. I'm going to draw a picture. We observe, more triangles than we would expect, than expected without a trilect effect. And if we had more edges, right? But also it's possible, again, wave, not a particle. So it's possible that we have a few edges. So if we look at the probability density function for the network, for the, say, number of edges, you just have like it's density of the network or something like that. Yeah, let's call it density. Density, right, the probability. Now, this is the probability distribution, right? And now, the expected value of this distribution may in fact be, and okay, maybe actually let me write a little different. Theta that would on average produce the number of edges and number of triangles that we observe. However, the model says that either you have the model would say that either you have, again, there's this positive dependence, which means that either all the edges are present or almost none are, right? Because once you start have edges, they get more edges, right? They're positively correlated. So any given network you generate from this model, you will either have very few edges or a ton of edges, right? Now, what does it mean? What does it mean? What do we call it when a model has a very low probability of actually producing the data that we observe, relative to other possible data sets? Well, we call it lack of fit. We use goodness of fit tests for that. We'll use logistic regression. Yeah, we use goodness of fit tests. We say, hey, it's unlike like this. This model does not fit the data well, even though this is the best possible estimator, maximum accurate estimator. It doesn't fit. So really, what we're saying is we're unlikely to see the network we actually observed under this model, even if we had a perfect way of estimating the maximum accurate estimator. So it's a bad model. Now, and in that respect, this simulated degeneracy is a symptom of the fact that we're using an estimation method like pseudo-maximum accurate estimator that does not realize, that produces an estimator that is not very accurate, and and does not take into account this effect, and the difficulty estimating the model comes from the fact that it's really hard to do a proper MCMC sampling of this, right? So in this case, I would argue that what people call degeneracy is just a poorly specified model, lack of fit, and degeneracy is just a symptom. There are other ways to have a lack of fit. Now, I don't have the picture here, but back when I was working on valued ERGMs for counts, unbounded counts, I actually saw a similar phenomenon, except because we have Poisson type thing, you have the 1 over x factorial bit in the denominator, which grows quicker than any exponential function. I actually ended up with this kind of a bimodal distribution that was both modes are very nice, almost Gaussian, but there were two of them, and the actual MLE was somewhere in between, or the actual observed graph was somewhere in between. Not MLE again. So that's my spiel on degeneracy and how I think about it. So to conclude, again, I apologize, I'm a bit over. So think globally and locally. Both of those are very useful ways of thinking about it. Right? ERGMs reproduce global features, but also have a local interpretation that can tell us a lot about how both we can, to a point, interpret the underlying social process, but also about its big picture behavior. Don't forget lessons for regression. Again, I implemented this detection, multi-entity detection, and I've been improving it ever since. And we tried, but nothing is perfect. What's your zeros, right? There are different kinds of zeros. Again, I only talked about it briefly. I could talk a lot more about observational stuff, but I only have an hour and a half. Degeneracy is lack of fit, at least. Again, this is a very general statement, but I think in almost all cases when we talk about degeneracy, it's just a bad model. Well, thank you for Universal Global Ventures for funding the flight here and back from the hotel, and of course, thank you all for coming. Thank you all for inviting me. These are references. I'm just going to put them on so they go on tape. Okay. Well.